Hi, welcome to Chapter 2 of Anatomy Physiology 1. This chapter is going to be chemistry. So my job is to cram a whole year of chemistry into about an hour to 2 hour talk. So obviously we're not going to go into great detail, but there are certain things that you do need to know. If I were you, I would stop this video right now and I would go find a periodic table that looks something like this one. The periodic table that you pick should have numbers like 1, 2, 3, 4, 5. It should have capital letters on each of the blocks, and it should have a little number right here over the abbreviation for the different element. And that's the atomic weight, or the atomic mass as it's called. Mine has a key down here that says this is the atomic number, this is the atomic weight, this is the symbol, or the abbreviation. And mine's a little fancy because it also has oxidation states, which are those teeny tiny numbers that are right underneath the atomic weight. All right, hopefully everybody has a copy of the periodic table right now. You can usually find it inside of your textbook, in the appendix, somewhere like that. Now we're going to spend some time learning to maneuver around the periodic table. Whenever I give a test over chemistry, I always give my students a copy of the periodic table. Rather than try to memorize all of this stuff, it's so handy just to have this sheet and know how to navigate your way around it so that you know what all the different things are. And it's amazing how easy chemistry becomes when you have a periodic table in your hand. All right, so the first thing you probably need to know is that every element, every individual atom, is made up of protons, neutrons, and electrons. A proton has a positive charge. A neutron is neutral, meaning it doesn't have a positive or a negative. But come to find out, it actually has one of each, so they cancel each other out. And then the electron is negative. The identity of each element is how many protons it has. So hydrogen is a gas. It's the lightest of all the atoms. It's so light that most of the atoms don't even have a neutron. It's just a proton and an electron, and that's all there is to it. So it's very simple and very light. And it has one proton, and its atomic number is 1. Helium is also a gas. It is so light that it floats in the air. It has 2 protons, 2 neutrons, and 2 electrons. Now, if you notice, there's a number 2 there, and I just said there's 2 protons. So hydrogen has 1 proton, helium has 2, and if you come over here to lithium, it has 3 protons, and its atomic number is 3. And beryllium has 4 protons, and its atomic number is 4. So I'm hoping that you guys are seeing a trend here. Boron, carbon, nitrogen, oxygen, you've heard of all of these elements. But now we're going to look and see where they exist on the periodic table and how that helps us know the characteristics of each of the different atoms. If you look at the abbreviations for the atoms, H is for hydrogen, a capital H with a lowercase e is helium, a capital L with a lowercase I is lithium. So anytime there are 2 letters, you have to make the first one uppercase and the second one lowercase. And this is really important because if we look at, for example, cobalt, which is a big C and a little O, that's the abbreviation for cobalt. But if you were to make a mistake and put a big C and a capital O, then what you just drew was carbon and oxygen, which is carbon monoxide. So big C, big O is carbon monoxide, and big C, little o is cobalt. And then you see some things that don't make any sense at all. For example, sodium is S-O-D-I-U-M, and you abbreviate it Na. Well, everyone else in the world calls this natrium, but here in America we call it sodium. So Na is short for natrium. And potassium is a K. So everywhere else in the world it's calcium, and that's why it's abbreviated with a capital K, but we call it potassium. When you get down into lead, which is element number 82, it's Pb. So the actual, everywhere else, it's called plumbium. Like plumbers, plumbers use lead pipes. They used to, anyway. They don't anymore because it's poisonous. It causes brain damage if you ingest it. So a long time ago, long before we knew about protons, neutrons, and electrons, there was a guy named Mendeleev, and he started looking at the properties of the different atoms, and he laid them out in a periodic table. And what was interesting is he left boxes empty. And he said, they're going to discover this element later. And he left other boxes empty and said, then they're going to discover this element later. And we did. So then the question is, how in the world did he put the atoms in order in the periodic table by properties when he didn't know anything about protons? And how in the world did he guess that in the future they would discover other elements and actually leave places for them? So that's one of the things I like about science. I call it woo-woo science, like woo-woo, that's pretty weird. So I just remember when I learned that in class and I thought, oh my gosh, that's so strange. So again, if we're in America, we weigh things in pounds. And if you're pretty much anywhere else in the world, they weigh things in grams. And in the scientific community, they weigh things in grams and kilograms. And then when they started trying to weigh atoms, they realized that that was kind of silly because an atom is so very, very, very small that you end up with it weighing, 0.0000000 something something. And that's just too awkward. So they said, why don't we make atomic mass units? And we'll just say that a proton weighs 1 and a neutron weighs 1 and the electron unfortunately weighs 1/1800ths. So they said, when you divide 1 by 1,800, it comes out to be such a small amount that we're going to ignore the weight of the electrons. So electrons do weigh something, but they weigh so very, very little that we pretty much just ignore it. And the example I always use with my students is if you stand on the bathroom scales and you weigh 100 pounds, and then somebody hands you a feather, how much do you weigh? Well, you weigh 100 pounds plus the weight of the feather, but the weight of the feather is so slight that it doesn't actually move the scales at all, and so it still looks like you weigh 100 pounds. So when we're looking at the weight of an atom, all we have to do is add the protons and the neutrons, and we know how much the atom weighs. And like I said, we're going to ignore the electrons. They do weigh something, 1/1800ths, but that's not enough to worry with, so we just ignore it, kind of like the feather or the piece of lint that fell on us when we were on the bathroom scales. So, how do you figure out how many neutrons there are? So I know exactly how many protons there are because it tells me right there. There's one there, there's 3 there, there's 12 there, there's 22 with titanium, and chromium has 24, iron has 26. So I know how many protons each one has, and I know each one weighs 1. So this one, the weight of the electron, or excuse me, the weight of the protons is 11, because 1 times 11 is 11. So then if you look at this little teeny tiny number right here, it is 22 point something 9. So we're going to round that off to 23. So if I were to hand you an atom of sodium, it would weigh about 23 atomic mass units. I know that 11 of that 23 weight is due to the protons, so that means that the other 12 has to be due to 12 neutrons. So if you just look at these two numbers and subtract them, you can tell how many neutrons each of these atoms has. So this one has 12 protons, and the atom itself weighs 24 AMU. So the other 12 has to be from neutrons because the electrons don't weigh enough to worry with. Now, you'll notice that it's pretty much that way, 12, 24, 11, 22. It's almost double, so it's about half protons and half neutrons. But then you get down here to some of these heavier elements, and palladium, 46 protons, but the atom itself weighs 105. So you've got more neutrons than you do protons. And the further you go, the heavier the atoms get, the more neutrons that they have to stabilize them. Here is mercury, and it has 80 protons. It weighs 200, so 120 neutrons for the total atomic weight. Now, you cannot take away a proton. You can take away a neutron. So we're going to talk about that in just a second. But here's one of the funniest things that I find very interesting. One of the reasons that people studied chemistry at all was to try to figure out how to turn all of the different metals out there into gold. That was the goal of the alchemist. So here's gold right here, AU. It weighs 79, it has 79 protons, and it weighs 196, 197. So, what would happen if I took mercury, which has 80 protons, and I knocked one of the protons away? What would I have? Well, if you have 80 and you knock a proton away, you have 79. And all of a sudden, you've taken mercury and turned it into gold. So now we know how to do it. We know how to turn different elements into gold. So if you ever go to the dollar store and you buy a thermometer that's full of mercury, if you had a machine that could knock off one proton off of each of the mercury, then you'd end up with a tube of gold. So a long time ago, probably back before you were born, money was backed by gold. And they had money in Fort Knox and various other places hidden away. And theoretically, you could take a piece of paper that said $1 or $5, and you could go and get that much gold. So we backed up all the money with gold. And I'm wondering, it was about the time they discovered that you could just knock a proton away and turn mercury into gold, that we went off the gold standard. And we back up our money with something else and not gold anymore. So, I don't know. One of the things that makes me nuts is I have so many accounts for so many things, and you have to come up with a unique password, and you have to keep changing your password. It seems like every couple of weeks. So here's somebody I thought that was rather clever. He used the periodic table, and he made a word using the letters on the periodic table. In this case, he made pancakes, and protactinium is element number 91, nitrogen is element number 7, calcium is 20, potassium is 19, and einsteinium is 99. So if you take these numbers, there you go. You have a unique password, but if you forget it, all you need to do is pull up the periodic table, and there's the numbers that make up your password. So anyway, I just thought that was kind of interesting. So I've told you that the protons give each of the atoms its identity, and we'll talk a little bit more about what the identity of each atom is in just a second. It wasn't until about 100 years ago that they discovered, actually less than 100 years ago, that they discovered that the protons and the neutrons are in the middle of each atom, and the electrons orbit outside. So if you can envision a football field and you put like a tennis ball on the 50-yard line, in the middle of the 50-yard line, and then you go way, 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 way out, as far out in the bleachers as you can go, and you put a ping pong ball. That's kind of the distance between the atomic nucleus and the first electron. So if you could blow an atom up to the size of a football field, the nucleus would just take up a little space on the 50-yard line, and the electrons would be at the outer bleachers. So an atom is mostly empty space. So one of the things students usually ask me is, well, then why can't we walk through walls? Well, the problem is the electrons are the things that are on the outside of the atom, and they repel other electrons. So as soon as you, with all of your electrons on your outside of your atoms, come up to the wall, which has its electrons on the outside of its atoms, you're going to repel each other. So the wall is going to push against you, and you're going to push against the wall. To kind of get a feeling of what that's like, in your mind, take a magnet and put the North Pole next to the North Pole, and it'll actually push. You can feel a force that's pushing you apart, the two magnets apart. But then if you turn it around and the North Pole and the South Pole face each other, then they're attracted to each other. So you get kind of a situation like that when you're looking at an atom. So I put this little picture here because I thought that was cute. The protons and the neutrons are in the middle of the atom, very, very close together, attracted to each other. And there's the electron way, 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 way off in the distance. So chemistry is the study of the different atoms. And then if you put these atoms together, and we're going to talk about bonding in just a minute, you're going to end up with biochemistry, or the atoms that we need to make up our body and to do chemical reactions within our body. So the study of chemistry as it applies to humans and other living things is called biochemistry or life chemistry. And we're going to learn about macromolecules, big molecules that have lots and lots of atoms that are sharing electrons. They're bonded together. And you are familiar with the 4 groups of macromolecules, because if you look on pretty much any food, if you look on a candy bar, if you look on a box of crackers, whatever it is that you're looking at, you're going to find that, especially again in America, that you have to put how much carbohydrate is in that particular food, how much fat is in there, how much we call it lipids, and how much protein are you going to get. You even have to do it on something like a Diet Coke or a Diet Pepsi or whatever, where you get no carbohydrates, you get no fats, you get no proteins. You just get some artificial sweetener and carbon dioxide and water, and that's pretty much it. And some sort of a phosphate or something to give it a flavor. So you are familiar with the 4 groups of macromolecules: the carbohydrates, the fats, the proteins, and the nucleic acids. Now, since all living things have DNA or RNA or both, ATP, the nucleic acids, you don't have to put the nucleic acids, because if you eat anything that was ever living, if you don't run around eating rocks or something, then you're going to get all the nucleic acids that you need. But you do need to know about how many carbs there are, how much fat, how much protein. These macromolecules, if you understand the structure of them, then as we go through the various chapters and we start talking about how we make urine, this chemistry will be very valuable. When we start talking about how we make ATP energy to power our bodies, this is going to be important. We talk about electron transport. There's so many places that we need this chemistry to talk about it. So I love chemistry, but I know that some students kind of feel about chemistry the way they do about math, and they just as soon not have it. I do think it's sad because, like I said, I find chemistry fascinating. But anyway, so here are some of the outcomes that you're expected to be able to do. You're supposed to, if I hand you a periodic table and ask you to find hydrogen, you should be able to look around and find hydrogen on the periodic table. You need to know what's the difference between an element and a compound. Well, anything on the periodic table is an element. So oxygen, nitrogen, helium, all of those are elements. And they can't be broken down into anything except for protons, neutrons, electrons. But a compound is several atoms stuck together, at least 2 or more atoms stuck together. When we look at the properties of the various things on the periodic table, some of them are going to be gases, some are going to be metals, and some we're going to call minerals. And we need certain minerals. You need vitamins and minerals in order for your body to function correctly. We're also going to learn about radioactivity and ionizing radiation, ions, electrolytes, free radicals, and different chemical bonds. We're going to talk about at least 3 different types of chemical bonds. We've mentioned that the atomic number is the number of protons that you find in the nucleus of an atom. But one of the things we didn't mention is for every proton you have an electron, because a proton is positively charged and an electron is negatively charged, and you have to have the same number. Otherwise, the atom or the element is going to be charged. You're going to have too many positives, you're going to have too many negatives, so you're actually going to have it out of balance. So for every proton, you're going to have an electron. Now, when we talk in just a second about the neutrons, we've already said you can have different amounts of neutrons. So we will spend just a moment about that in just a second. Now on this one, it's talking about all of the elements are arranged by their atomic number, which is the number of protons, and they either have 1 or 2 letters. The first is always capitalized. The second, if there is a second letter, is always lowercase, has to be. Now, interestingly enough, out of that whole periodic table, there's only about 24 of them that make any difference whatsoever in our body. And of the 24 elements, really almost every single bit of us, 98.5% of us, is oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. So those 6 elements make up almost every single bit of us. And then we've got a little bit of iron in there because we need iron in our blood. We need some copper because that makes some of our enzymes work. So there are some trace elements that we have in our body, but we're pretty much this. And I'm sure that you've heard that water is H2O. So we're mostly water. So there's your hydrogen and your oxygen. And carbon is a very versatile atom. In fact, there are 2 classes that you can take in college, which are called organic chemistry. And for a year, they talk about carbon compounds. Can you imagine taking 2 courses where you're talking about carbon? Amazing, but fascinating. So it is that versatile that you could actually spend all that time talking about all the things you can do with carbon. Nitrogen is going to make up our amino acids. And it's interesting, when you finally die, one of the things that kills you is a buildup of nitrogen in your bloodstream. So I was always amazed when a doctor would say, it's time to bring everybody to the bedside because grandma's going to pass away tomorrow. I'm like, how do they know that? How can they tell that? Well, unless you're hit by a car or something like that, almost every single person who dies from a buildup of nitrogen, but they don't put that on your death certificate. They say, well, you died of cancer or you died of something else. But generally it's because you can't get all the nitrogen out of your bloodstream. So anyway, that's kind of an interesting thing. I thought I'd throw that in there. Calcium, of course, is what you build up your bones with, and phosphorus, the same thing. And when you talk about ATP energy, the P is phosphate. So this is going to be really important for our energy-making compounds. I'm sure you've heard of lithium batteries, and we need a certain amount of lithium in our bodies. And in fact, some of the people who had some mental illnesses, come to find out they were just deficient in lithium, and if you gave them a little lithium, it fixed them. So that was kind of surprising. So some of the other, we won't learn all 24 of the atoms that make up our body, but some of the ones that we're going to be really talking about are chlorine, like sodium chloride, and magnesium, calcium, sodium, and sulfur. So sulfur is going to be important because it holds our proteins together. And sodium and potassium are how we make our nerves and our muscles work. We have sodium and potassium, we charge up the cells almost like you charge a battery. And then it runs down, you use your muscle, you use your nerve, and then you have to recharge it. So sodium and potassium are very important. Potassium is used for euthanasia. If you have a pet and you take it to the vet and you need it to be put to sleep, that's what they do. They give it some potassium, because if you have too much potassium, your heart can't beat. And if you have a lethal injection, you know, people that are on death row and they give them a lethal injection, they give them potassium and it stops their heart. So too much potassium is dangerous. Not enough potassium is dangerous. So we're going to learn about the homeostasis and the balance between these ions as we go through the various chapters. There is a lot of stuff on this particular PowerPoint slide, but it's only been about 100 years that we had an idea that the atoms were kind of like spherical, kind of round, and it wasn't until almost World War II that we knew about the nucleus of an atom. So a lot of this is new material, surprisingly enough. If you could see the nucleus and then you could see the electrons orbiting around it, kind of like the planets orbit around the sun, it kind of gives you a feel for what the atom looks like. But it's not exactly correct. So the true chemist will put their nose up in the air and they go, oh, that's a horrible analogy. But for us, since we're not chemists, it works great. Here's the stuff about the 1 AMU, that the protons weigh, neutrons weigh 1 AMU, and electrons have such a low mass that we ignore it. So here's the slide that talks about that. And we're going to be looking at the electrons because although they're tiny, they make up the reactivity of each of the different atoms. So they're going to turn out to be super, super important. So in a minute, we're going to be talking about quantum chemistry. If you were to look at the orbits of the electrons around the nucleus, you would find a kind of an interesting phenomenon. If you have an electron, it will try and go towards the nucleus of the atom because positive and negative are attracted to each other. But in the case of, let's say, helium, here are 2 electrons. I know there's 2 electrons because there's 2 protons. For every positive, you have to have a negative. So I have 2 protons and 2 electrons, and they're going to be trying to get close to the middle of the atom, but they can't get too close because as they get closer to the middle of the atom, they're going to run into each other and they're going to repel each other. So they come to an equilibrium. So they're as close to the nucleus as they can get without interfering with each other. So they're repelling each other. And then if you come over to lithium, you've got 3 protons and you have 3 electrons. And lo and behold, when you look at where the electrons are, they're not swarming in a set of 3 around the nucleus. You've got 2 of them that are close to the nucleus, and there's 1 that's a distance away. And that was kind of surprising. So this is why they say that the Bohr model isn't the greatest of all the models, because it just kind of gives you a feeling that all the electrons can just be swirling outside of the nucleus. But if you actually look, there's almost like an energy level. And here's a picture of someone who tried to show you about the energy levels. So here's the nucleus of an atom. Here's the nucleus. So here's 3 different atoms we're going to be looking at. And if you look, here is kind of a path. And these are electrons, but they cannot get any closer because they're going to repel each other. So in this first energy level, you can put 2 electrons, and you can't put any more. And then you jump out, and you have an energy level that can hold up to 8. And if you go even bigger, then here's the 2 that you can have close to the nucleus. Here is the 8 in the next energy level. And then you jump out and you have a 3rd energy level, and it can fill up with about 8 electrons. So when they talk about quantum levels or these jumps, discrete energy levels, this is what they're talking about. Now, if you were coming in towards this particular atom, The only electrons that you're going to bump into are the ones that are in the outer energy level, and we call them valence electrons. So in the case of nitrogen, we have 2 in the middle, right here, that are orbiting close to the nucleus. And then since we have 7 protons, we have a total of 7 electrons. So 2 are here, which means you've got 5 left over in the outer energy level, right there. So if they ask you, nitrogen has 5 valence electrons, or 5 electrons in its outer energy level. And that's going to be super important in just a minute. If you look at carbon, it has 6 protons in the middle, and so it's got 6 electrons. 2 can fit in the first energy level, and since there's a total of 6, if you take 2 away, that means there's 4 left over in its outer energy level, right there. And then if you jump down to sodium, it has 11 protons, so it has 11 electrons. And you put 2 in the first energy level, because that's all you can get in, squished up close to the nucleus. And 2 from 11 leaves 9. Well, the next energy level can only hold 8. So here are the 8 in the next energy level. So 2 and 8 is 10, but we need to put 11. So that leaves 1 lone electron out in the third energy level. So we're jumping energy levels. Now, what's unfortunate about this particular picture and anything that you're going to find in a book is it's flat. And we know that spheres are not flat. So in your mind, I need you to take these electrons, and instead of having them go around and around in a circle in a flat plane, I need you to have them come out towards you and back behind the screen in all different directions, not just round and round in a flat circle. And the same thing with these. They're not just in one flat plane. They're coming out at you, they're going back behind the screen. So if you can visualize that, it'll help you a lot in seeing atoms. Again, a lot of people like our solar system because we don't just have a flat plane with the sun in the middle and then all of the planets circling in a flat orbit. So anyway, it's hard to get a mental picture of something you cannot see, that is too tiny to see. So if I ask you to draw me an atom of, let's say, magnesium, in the nucleus you would put 12 protons because magnesium has the number 12. And because one atom weighs 24, you would also in the nucleus put 12 neutrons. So you can have 12 protons and 12 neutrons for a total weight of 24. And then you're going to have 12 electrons that are orbiting outside in the energy levels. So what would that look like for 12? Well, you put 2 in the first energy level because that's all it can hold. And then you come out to the next energy level and you can put 8. So I have 2 in the first, 8 in the next for a total of 10. And now I have to put 2 more electrons. And so I'm going to go to a third energy level and I'm going to put the last 2 electrons. So magnesium has 2 valence electrons. And you can tell me just by looking at this 12 and this 24, all of those things. All you need are those 2 numbers to tell me all sorts of information. We looked at sodium. Let's look at beryllium. Beryllium is a lot simpler. It has 4 protons. And if you look carefully, it weighs 8. So you're going to have 4 protons. you're going to have 4 neutrons in the nucleus, and you have 4 electrons. And you're going to put 2 electrons in the first energy level, because that's all it can hold. And you have 2 left over that are going to be in the next energy level. So it has 2 valence electrons. Now, if you remember, you can rewind your YouTube video, or remember that magnesium also had 2 electrons in its outer energy level. And interestingly enough, if we go down to calcium, it has 20 protons. It weighs 40, so it's got 20 neutrons, so 20 plus 20 is 40. It's got 20 electrons, so it's got 2 in its first energy level. It has 8 in its next energy level. It has 8 in its next energy level. So 8 plus 8 is 16, plus 2 in the middle is, 16. 8 plus 8 is 16, plus 2 is 18, which leaves me 2 left over for the 4th energy level. Do you think it's a coincidence that beryllium has 2 electrons in its outer energy level? Magnesium has 2 electrons in its outer energy level. Calcium has 2 electrons in its outer energy level. It's not. So you're going to find that the columns tell you a lot about the electrons in the outer energy level. And look at what column this is. It's column number 2. So those of you who know Roman numerals, it's Roman numeral 2. If you go over here to this column, these all have 1 electron in their outer energy level. So if you don't believe me, draw them out. So lithium would have 2 in its first energy level, and that third one would be all by itself in the outer energy level. Hydrogen only has 1, so it's got 1 in its outer energy level. Sodium has 1 in its outer energy level. We looked at that. So you can look at the number up here, or you can draw it out and figure out which energy levels. But the only electrons that we're really interested in are the ones in the outer energy level, the valence electrons. And it's very easy to look and see what column that they're in. Or here's where this particular periodic table is pretty cool. If you look right over the hydrogen symbol, there's a little 1. And if you look over the lithium, there's a little 1. So that tells you how many electrons there are in the outer energy level. Look at that: sodium, potassium, rubidium, cesium, francium, 1. Beryllium 2, magnesium 2, calcium 2, strontium. Now, here's one of the things that I find interesting, and I keep wanting to take some of the higher level chemistry classes to see if they've ever figured out what's going on right here. But these guys right here are called transition elements, and they don't play by all the rules. So I'm giving you the general rules for how many electrons are in the outer energy level and what make up the valence electrons. But these guys don't always play by the rules, so we'll come back and talk about them in just a minute. So here's group 1, here's group 2. Ignore these guys. Jump over here to 3. And these have 3 electrons in their outer energy level. These have 4 electrons in their outer energy level. 5 electrons, 6 electrons, 7 electrons, 8 electrons in their outer energy level. So these guys play by most of the rules, and these guys do, but the transition elements are a little bit weird. So let's look at them just briefly, but that would be something you would take an advanced chemistry class to talk about them. Look at the number. So here's 1, here's 2, here's 3. And titanium has 4, which we would have expected because it's in column 4. But it also has a 3 beside it. So because of the way the orbits are in that, it can either act as if it has 4 electrons in its outer energy level or 3. And then we would expect this one, vanadium, to have 5. And it does, but it also has 4 and it has 3 and it has 2. So if you look, all of these, let's look at magnesium. Or excuse me, manganese. Everybody says manganese and magnesium interchangeably, but these are manganese, is not magnesium. It has, sometimes it has 7 in the outer energy level, sometimes 6, sometimes 4, sometimes 2, sometimes 3. So it changes. Iron can either have 2 or 3 in its outer energy level. Nickel, copper has either 2 or 1 in its outer energy level. So most of these transition elements can act as if they have 2 electrons in its outer energy level. And then something else. 2 and 1, 3 and 1, 2 and 4. So like I said, the transition elements are weird. But it's nice to have these little numbers because it will tell you, when we get into bonding, how they're going to bond. So let's stop and talk about something that you may have been noticing I have glossed over and haven't really mentioned. Let's look at titanium. Titanium has 22 protons, 22 electrons, because you have the same number of protons as your electrons, but it weighs 47.9. Now, how can you weigh 47.9? So we have a little problem here. So let's do a little stopping and looking. If you ask somebody how many children are there in the average American household, they're going to say something like 1.8 children. So I just asked Alexa, and she says there's 2.1 kids in each household. Well, obviously you can't have 2.1 kids. So if you look at one household, it may have 1 child. Another household may have 8 children. Another one may have 4. Another one may have 3. You may have a whole bunch that have 2. In each household, there's 2 there and 2 kids in that one and 2 in that one. But when you take it all together, the ones that don't have any children, the ones that have 10 children, and all of that, and average it out, you're going to end up with about 2.1 kids per household. So when you are weighing atoms, you're going to pick up an atom of titanium, and it's going to weigh 47. And then you're going to pick up another atom of titanium, and it's going to weigh 48. And you may pick one up and it weighs 46, and you may pick up one and it weighs 49. But you're going to find that almost all of the atoms of titanium that you pick up are going to weigh close to 47, 48, because 47.9 averages off to be 48. So, how can this be? Well, you cannot change the number of protons, because if I change the number of protons for titanium, I would suddenly end up with either scandium or vanadium. So I can't change that. I can't change the number of electrons, because if there's 22 positively charged protons, there have to be 22 negatively charged electrons. So the only thing I can actually change are the neutrons, and they're neutral. So you're going to find that some of the atoms are going to weigh 47, so they're going to have 22 protons and 22 protons and 45 neutrons, or 22 protons, and if this was 48, that would be 26 protons. So the number of protons can vary, and we call this isotopes. So the definition of an isotope is an element that differs by the number of electrons that it has. So if you add more neutrons, each one weighs 1, and so it's going to increase the atomic weight. If you take neutrons away, then you're going to have a lighter atom. So they are still chemically similar because they have the same number of valence electrons. And they're going to keep their identity because they have the same number of protons. So the valence electrons don't change in an isotope, nor does the number of protons, the number of positive charges. So those don't change. Now, if you were to look at somebody, I always like to do this when I'm teaching a lab, I have somebody holding books, and you put one book in their arms, and you put another book in their arms, and you put another book and another book. There comes a time where the person can't hold all the books that you're putting in their arms. And so they're going to start dropping the books. And the same thing is true of the nucleus of an atom. There's only so many neutrons it can hold. And if you try to put any more neutrons in than it can hold, then some of the nucleus is going to fly apart. And if you happen to be standing in the path of a piece of flying nucleus, we say that you got hit with radioactivity. So a radioactive isotope has the wrong number of neutrons. And it doesn't necessarily have to be too many neutrons if you don't have enough neutrons in there. So if you go too far the other way, then the nucleus becomes unstable, and energy and particles will fly out of the nucleus to try and make it come back to equilibrium. So all atoms have isotopes. All atoms have isotopes, but not all isotopes are radioactive, because sometimes the nucleus is perfectly happy having just 1 or 2 extra neutrons, and it doesn't have any trouble accommodating them. But again, you're going to reach a point where you try to put too many neutrons in or try to take too many neutrons out, and now the nucleus is unstable, and now we say that particular atom is radioactive. So here's a slide showing the isotopes of hydrogen. So most hydrogen is simply 1 proton and 1 electron. It's the simplest of all the atoms. But if you were going through a big pile of hydrogen atoms and picking through, every now and then you're going to find an atom that has a proton and a neutron and an electron. And then if you really keep looking and really keep looking, every now and then you're going to find one that has 1 proton, 2 neutrons, and 1 electron. So you notice in each case, 1 proton, 1 electron, 1 proton, 1 electron, 1 proton, 1 electron. You have to have that so that it's electrically balanced. But you have no neutrons, 1 or 2. But this is not stable. You've added 1 neutron too many. So an atom of hydrogen that has 2 neutrons is radioactive, and we call it tritium. So here's a slide that kind of summarizes what we've been talking about. Every element has at least 1 radioactive isotope. You can send electrons flying out. You can send whole alpha particles out. You can send out X-rays. You can send out beta particles, gamma radiation. So you've probably heard about gamma radiation. One of the things that spies apparently like to do is get radioactive alpha particles, because they're such a low level radioactivity that you can handle it. It can't get through your skin. So you can just carry it around, and you can kind of dump it into somebody's drink or pour it on top of their food and then walk away. And the person eats the food or drinks the drink that's got radioactive alpha particles in it. And if they're on the outside of you, your skin protects you. But if they're on the inside of you, they start destroying all the stuff inside your body, and then you die of radiation poisoning. So for a while there, if you read back in the news, that was one of the ways that spies would kill each other, with alpha particles, radiation. And there's not much you can do for somebody who's drunk some alpha particles. We use gamma radiation to destroy cancers, and if you look around, you can find doctors that use a gamma knife, so they can actually use this radiation to cut you open and remove things. So even though radioactivity is dangerous to us, we have been able to harness it to do various things to help us out. One of the hardest things for people to comprehend is that all of us are radioactive. We're only slightly radioactive, however, because remember, we have carbon inside of us, and some of the carbon that's inside of us is radioactive. We have nitrogen, and some of it's radioactive. We have oxygen, some of it's radioactive. So we have a certain amount of radioactivity within us. And as long as we're eating things that have radioactivity in them. So we're constantly replenishing the radioactivity. Now, the thing with radioactivity, like I said, particles come flying out and energy comes flying out of the nucleus. And after a while, they're not radioactive anymore. They've reached equilibrium. They've gotten rid of the extra stuff that was making them unstable. And so now they're okay. So we call it a half-life. And that's how long it takes for half of the radioactive atoms to not be radioactive anymore. So some of them, it's a matter of minutes. Their half-lives go through, and every couple of minutes, it loses some of its radioactivity until in a very short period of time, it's not radioactive anymore. There are other things that have such slow decay rates that it may take 4,000 years, 5,000 years, 10,000 years for half of it to not be radioactive anymore. So one of the things that we've discovered is we know that when you die, of course, you stop eating. And so you stop taking in radioactive particles. And so from now on, as you decay, so do the radioisotopes inside of you. So we know how much, say, radioactive carbon you should have inside of you if you're alive. And then if they find your body 10,000 years from now, like happened, they found somebody who had fallen into the ice in the Alps and was frozen. And of course he died because he was frozen in the ice. And they took his body and they were able to say, okay, well, if he was alive, this is how much radioactive carbon he would have in him. But now he has so little radioactive carbon that we know that he died 10,000 years ago. So we can actually use the radioactive isotopes that are in our body or in the things that we find that we dig up, in ancient Greece and Rome and places like that, and tell you how old they are, because we know how much radioactivity they should have, and we can see how much of it has gone through half-lives. So I'm going to stop here and leave you with a joke that I thought was kind of funny. If you look at the symbol for oxygen, it's O, and if you look at the symbol for magnesium, it's Mg. So, did you hear that oxygen and magnesium got together? OMG.